you can enjoy walking at a constant velocity. That means my initial or starting velocity is the same as my final velocity. Since my velocity doesn't change over time, my acceleration is zero. With this given information in the kinematic equations, I can predict how fast, how far, and for how long an object is traveling.
When you're walking at a constant velocity here on Earth, you can plot your motion on our three graphs: position, velocity, and acceleration versus time. On a position versus time graph, our slope tells us our velocity. If I'm moving forward, I have a positive slope because I've gone from my origin to a forward position. If I'm moving backwards, I'm starting from further ahead from the origin or starting place and moving backwards in position. Positive slope is forward, negative slope is backwards. The slope from that position versus time graph informs our velocity versus time graph. Because we're talking about constant velocity, our final and initial velocities are the same, which means that we have horizontal lines. If that horizontal line is above the x-axis, we're going forward. If it's below the x-axis, we're going backwards. But notice it starts and ends at the same velocity. That's how we get a horizontal motion. Since we're moving at a constant velocity, we're not changing velocities. If we don't change velocities, we have no acceleration. If we have no acceleration, it's right on the x-axis, just like if the object was stopped.
These are the kinematic equations. We use them to predict motion. They're derived from the relationships between distance, velocity, time, and acceleration. Before we can use a kinematic equation, we need to choose a kinematic equation. This flowchart makes it simple. At the very top, you're asked, which variable is not included in your list of given information? There are four options: distance, final velocity, time, and acceleration. Once you've established which variable is not included, there are two options for calculating your unknown variable. If you substitute your given information into the original kinematic equations, you may end up solving for an unknown variable. Challenge yourself to use your inverse operations to solve for the unknown variable. If the variable is already by itself on the left-hand side, you'll have to follow the order of operations. Or, the other option, you can simply use the order of operations as long as you know which variable is unknown. The derived equations at the bottom already have the unknown variable by itself. So after you substitute in your given information, you can use the order of operations to evaluate for your answer. For example, say your final velocity was not included, and you're solving for acceleration. You could substitute into the original kinematic equation, plug in your time, your initial velocity, and your distance or displacement, and then use your inverse operations to solve for acceleration. You could also double check yourself using the order of operations. In this case, acceleration is already by itself. So when you substitute in distance or displacement, initial velocity, and time, you can use the order of operations to evaluate your answer. Let's try one together. If you're walking at a constant velocity of 2 meters per second, your initial and final velocities are exactly the same. You travel for 18 meters. And you want to know how long it takes you to travel that far. We need three given pieces of information, an unknown variable. This is usually what the question is asking for. How long did it take to travel this far? That fifth variable is not included. The variable that's not included is the key to finding your kinematic equation. In this case, acceleration is not included. So I have two options. First, I could substitute into my original kinematic equation and then solve for my unknown variable, time. To find the answer, I need to use the same problem-solving process we always use. I've already listed out my given information. Here's my equation. My general equation is my recipe. My ingredients are my given information. I'm going to substitute in. Initial velocity and final velocity are both 2. Time is unknown, and x, displacement, is 18. This gives me a multi-step equation. I need to simplify it before I can solve it. 2 plus 2 is 4. Half of 4 is 2. Now I have a one-step equation. What's happening to my variable? I'm multiplying it by 2. To undo that, I'm going to divide both sides by 2. This means it took me 9 seconds to travel 18 meters at a constant velocity of 2 meters per second. There's another way to solve this problem. Acceleration is still not included. However, instead of using the original equation and then solving for time, I can use an equation that already has time by itself. So I start over. My givens are listed. Here's my general equation. But when I substitute in, my variable is already by itself. So I just need to use the order of operations. When you have a big rational expression, simplify the top and bottom before dividing. 2 times 18 is 36. 2 plus 2 is 4. 36 divided by 4 gives me again 9 seconds. Whether you use the order of operations or challenge yourself to solve the equation, at a constant velocity of 2 meters per second, it takes you 9 seconds to travel 18 meters.
Newton's third law of motion states that for every action there's an equal and opposite reaction. Essentially, forces work in pairs. Walking is a direct application of Newton's third law. For example, when this bird pushes its foot down and back against the ground pushes up and forward on the bird's foot with the same force or pressure. Applying a steady rate of steps and the same amount of force per step creates constant velocity. Boston Dynamics has applied Newton's third law with their line of robots that can actually walk. Atlas, their most realistic and terrifying robot, can walk on 2 legs just like a human. The robot's computer brain knows how much force to apply to the ground as it steps. If it applies too much force to the ground will push back with that same amount of force and knock the robot over. If it applies too little force to the ground will push back with the same amount of force, and Atlas won't move forward at all.
As I walk forward at a constant velocity, there's a gravitational force pulling straight down on me. The surface I'm walking on is creating a perpendicular normal force pushing up on me. The surface is also rubbing against the surface of my feet, creating a friction force pulling back on me. This is because my feet are hitting the surface and creating an applied force forward. Because I'm moving at a constant velocity horizontally and I'm stopped vertically, all of my forces are balanced.
When we create a force diagram, we follow a couple steps. Step 1, identify the forces. What's pushing, what's pulling on the object. Every force has its own known cause. 2, is it balanced or is it unbalanced? Are these forces pulling the same amount or are they pulling in equal amounts, unbalanced amounts? With constant velocity, it's all balanced. 3, we need to calculate the forces. Anything that we're given to calculate, like our gravitational force, we need to calculate it out. And then 4, balance those force equations. If we know what our left equals, we can find our right because they're balanced. Let's draw a force diagram for a 75 kilogram person walking at a constant velocity. They're on Earth, so gravity's pulling down, so we're going to decide which forces are acting on them. Gravity. They're on a surface. A normal force is pushing up at a perpendicular 90-degree angle on them. Because of Newton's third law, when they step, the ground pushes against them, pushing them forward. This is an applied force, just a general push or pull. And as they drag their feet along the ground, they create friction, which pulls against them. Friction always acts against motion. Now that we have our force diagram drawn, we can start including some values. This is a 75 kilogram person, so we take their mass, 75 times gravitational force constant of negative 9.8. Remember, this is the acceleration of objects here on Earth, negative 9.8. Multiply that together and we get negative 735 newtons. That makes sense because gravity's pulling downward in a negative direction. Now I can find that equation. Fg, my downward force, plus Fn, my upward force, my opposing force. Because it's balanced, it has to equal 0. So opposites add to 0. If 735 negative is pulling down, 735 positive is pushing up on the person. Now we know that the applied force is 367.5 newtons. If that's 367.5 newtons forward, we know that those have to be balanced forces. FF plus FA equals 0. Opposites add to 0. So negative 367.5 newtons pulls back on the object. We made this force diagram by identifying the forces, which forces are pulling up, down, left, and right. Then we decided it's balanced because it's a constant velocity. Constant velocity is balanced forces. Based on that, we were able to calculate some forces like gravity. We were able to include the applied force and then use our balanced force equations. If we're pulling down with a negative 735, we realized we had to be pushing up with positive 735 because those two forces, when added together, need to equal 0 because they're balanced.